how should we define differentiability of a multivariable function? Well, if you've seen the previous video in this Calculus 3 playlist, the video on partial derivatives, you might think that we've already got an answer. Partial derivatives are the higher dimensional analog of the derivative back in single variable calculus. But unfortunately, it's not quite so simple. And in this video, I really want to explore why we need something more than partial derivatives. So we're going to see an example where we're going to talk about continuity. And continuity is a very important property that a function can have. We're going to talk about whether they have partial derivatives and what the relationship between continuity and partial derivatives is. And then we're going to see that we're actually going to need an entirely new concept, one that we're going to call differentiability, that is separate from just having partial derivatives. And so that final answer about differentiability we're actually going to introduce in the next video in this multivariable calculus series. Now, before we dive into the multivariable situation, let me just briefly remind you of what was going on in single variable calculus so that we have something to compare to. Now, in single variable calculus, there was this very important relationship that if you had a discontinuity of a function, then the function was not differentiable. And then the counterpositive of that statement is that if you have a differentiable function, it had to be continuous. And an example that kind of illustrates this point is, well, the step function, the function that's 0 when x is less than 0 and 1 when x is greater than or equal to 0. This just, well, looks like this. It looks like a little step. Now, it's clearly not continuous at the point x equal to 0. There's this jump at x equal to 0. But nor is it differentiable at x equal to 0. If you think about what the derivative did, it was trying to put a tangent line on at some particular point. But how could you ever put a tangent line to the curve at the value of x equal to 0? And so this example was one such example where it was neither continuous nor differentiable. But look what happens in sort of the higher dimensional analog of this exact same function. So we're talking about multivariable calculus now, and the function we're going to talk about looks superficially very similar. It's 0 for xy not being equal to 0, and then 1 for xy equaling 0. Xy equaling 0 is just saying either x is 0 or y is 0. Those are the axes. And so this is what it actually looks like. It looks like a cross. Above the axes where x is 0 or y is equal to 0, the function has a height 1. Everywhere else, it has a height 0. Now, I really love this function because, as we're going to see, it helps to illustrate some of the core ideas of multivariable calculus. So let's try to answer the same questions. Is this function continuous? And does it have partial derivatives? Now, just looking at the function makes it appear that it's not continuous. Indeed, it's going from 0 and then it jumps right up to 1. And that kind of jump we think of as something being not continuous. But perhaps we should try and actually state that a little bit more precisely with limits. Because what is continuity? It means that the limit exists and the function exists and they are equal. So let's compute the limits of this particular thing. I want to take first the limit going to 0, 0 of this function f of x, y. Now, when we first introduced limits in this multivariable calculus course, we saw that we could do limits along a bunch of different paths. And so I'm going to first begin with a path which is going along y equal to 0. In other words, this is just the x-axis. Now, along this path, if you're going along the x-axis, well, that function is 1 everywhere where y is 0. So according to this path, this is just taking the limit of the function 1, and of course the limit of the function 1 is just, well, 1. So the point is that this path does not see anywhere where the function is 0. It only sees where the function is 1, and so it appears like the limit is 1. Okay, let me do a different path though. Now I'm going to take the path which has changed to be y equal to x instead. So these are numbers like 1, 1, half, half, 0.1, 0.1. But what is f of a number like 0.1, 0.1? Well, anywhere that was not an axis, we saw that it was 0. So along this path y equal to x, it's going to be, in fact, 0 everywhere, except for this case when x is actually equal to 0 and y is actually equal to 0, which the limit doesn't care about. And so, as a result, what is this limit of? This is the limit of things that are 0 unless just 0. Okay, so what's the big takeaway here? Now we've seen that, indeed, we have two different paths, and the limit along those two different paths gives two different values. And so the limit does not exist. If the limit does not exist, the function is not continuous, because continuity meant that the limit existed and equaled the function value. So in this case, we have proven that no, it matches our intuition, it is not continuous. Okay, so if what was true in Calculus 1 was true here, we would therefore be able to immediately say that the partial derivatives did not exist. That's what we might hope for. Fortunately, it's not quite so simple. So let's try to study the partial derivatives and see what happens to them. So let's do the partial derivative with respect to x first. So the partial derivative of f with respect to x and at the point 0, 0. So that's what the vertical bar means, evaluated at 0, 0. The definition of partial derivatives, as we've seen previously, is, well, it's analogously a limit. And in this limit, the function is evaluated at a couple different places. In the y-coordinate, well, it's just zeros everywhere. So in other words, the partial with respect to x is thinking of as the y value fixed and only changing the x. But then likewise, if you focus instead on the x components, well, the x components change. The one point we're evaluating has an x component of 0, and the other point has an x component of 0 plus h. It's being shifted by this little amount h that we're taking the limit of and assuming is going to 0. So this is our definition. Now, let's actually try to compute this. In this case, the x component actually doesn't matter because the y component is 0 in both cases. And this function is a function that if the y component is 0, then the function has a height of 1. So both of these expressions on the top are just the values of 1. This is just the limit of 1 minus 1. 1 minus 1 is 0. It's a little bit weird. You might think this is a 0 over 0, but it's not quite the same. It's a true 0 on the top and then something getting closer and closer to 0. So at any value of h that's non-zero, then we have 0 divided by something. Either way, it's always just going to be equal to 0. So this is surprising now. The partial derivative exists. It's equal to a specific number. And one of the ways that I think about this is, what does a partial derivative see? Well, it fixes that value of y equal to 0, and then it imagines the x values changing. It's only looking as you change the x values. It's only looking down the x-axis. But then the function down the x-axis is really nice. It's just a constant 1. And so the partial derivative, from what it can see, doesn't see any problems. To look at this a bit more visually, I've plotted the point, which is 0, 0, 1. That's what happens when you plug 0, 0 into f. You get a height of 1. And then likewise, if I plug in the point h0, that also has a height of 1. So those 2 points, I can put them down. And then what do I think of the partial derivative? The partial derivative is the slope of that secant line between these 2 points, and the limit as h goes to 0. But because these 2 points lie on a horizontal line, the slope between them is just 0, and another argument why this partial derivative makes sense to just be 0. Okay, that's the partial derivative with respect to x. The same argument applies for the partial derivative with respect to y. Nothing really changes except for the location of the h. So now the location of the h is in the y component. It's the x component that's fixed at 0 and the y that's got that 0 plus h. But by the same argument, it's 1 minus 1 and a limit of 0. So both the partial derivative with respect to x and the partial derivative with respect to y, both of those exist and are equal to 0. Okay, so what's our takeaway? We now have an example here that is discontinuous at 0, 0, but the partials exist at 0, 0. And so this is a different relationship. The relationship from single variable calculus that a discontinuous function meant it was not differentiable is not exactly valid, at least at the level of partial derivatives. It can be discontinuous, but the partial derivatives exist. So what this really motivates us is that we need a better notion of differentiability. And that is exactly what we will define in the next video.